the talk today will be drawn from 3 papers, joint work with Jean-Marie Meng and Leo Raisin, with Adam Smith and Leo Raisin, and with Ron Canetti, Omer Paneth, Adam Smith, and Leo Raisin. I'll try and reference where these things are. I'm used to people interrupting me during a talk, so feel free to interrupt me. I mean, ask questions. I guess just interrupt. Thank you.
Welcome to Israel.
And fortunately, a lot of what my first 10 slides are, Rita already covered this morning, so I'll try and breeze through them. So we're going to be talking about key derivation from noisy sources, just like we were this morning. So we consider, just to set terminology, we're going to consider an initial reading of some physical source, like biometric, that we'll call W0, that's not equal to a later reading W1. We're going to, for this talk, consider sources that are a sequence of symbols, so A1 through AK, and we'll assume a bound on Hamming distance, and we've covered Hamming distance already. It's just the number of symbols that differ between the 2 strings. So you can consider this in the binary realm or over an arbitrary alphabet. Okay. So our goal is to derive a cryptographically strong output repeatably from W0 W1. So they should map to the same output. This should look uniform to an adversary. And the goal of this talk is going to be to derive keys from physical sources that we haven't been able to handle before. So a lot of biometrics, we don't know how to get strong security out of them, but we also don't know that we shouldn't be able to. So I'll pin that down a little bit more as we go. Okay. So biometrics measure some unique physical phenomenon. We want them to be unique, collectible, permanent, universal, hard to steal. There's a lot of properties that you want. It's not clear that any biometric satisfies all of them simultaneously. Repeated readings usually exhibit significant noise. If there's no noise, then none of what I'm going to talk about matters. And the uniqueness in noise conditions varies widely between biometrics. This is probably a controversial statement, so I'll attribute it to somebody else. The iris is believed to be the best biometrics in terms of entropy rate versus it's easy to collect, but not something that is still somewhat private. You can collect it in different wavelengths, and the IR reading of an iris is more or less independent from the visible light reading. So you're not seeing my image on Facebook is not going to compromise the security of, say, if I took an IR reading. So it's possible that you can collect this under special conditions, but it's hard to take a fingerprint off of a table or something like that. So this is going to be a theoretical work, but I'll keep coming back to the iris as our use case, and I'll come back to whether we actually solve the problem for irises at the end. So just as an introduction for how irises work, I am not a vision person. I won't even pretend to be one today. So there's kind of 4 main stages in the processing of it. The first is we locate and we isolate the iris. We unwrap it into this second stage, which is just still pixels, but it's been kind of centered and normalized. Then we take a sequence of 2D wavelets at a sequence of positions. This gives us an X and a Y position, or a real and imaginary component for each of these positions. We quantize each of these, and this gives us this code right here, which is we normally think of as being 2048 bits long. It's estimated to have about 250 bits of entropy, and the error rate depends vastly on what conditions you collect it in. I've seen numbers as low as 3%, as high as 35%. I'll use the number 10% throughout the talk for error rate. Okay, so I just want to make a note. We're thinking of 2 different physical processes. The first is that the universe or God or whoever you want creates an individual, creates this baby right here. And then we take a reading from this baby. And this gives us some initial reading that we're calling W0. So this is a 2-stage process right here. The universe or God creates the baby, and then we take a reading from it. Okay, and that's our initial reading W0. So we think of W0 as a random variable that has both of these processes in it. Okay? And then W1, which is where we're getting our noise, we have this fixed baby and we're taking a reading from it. And the point I want to make is that our initial reading and our repeated readings may not be subject to the same noise. It may be possible, for example, an ID card to get a better reading the first time. So we don't want to think of these two error processes as exactly the same thing. And so what we're going to do is we're going to get our uncertainty, our entropy from this first process, this two-stage process, and our errors are going to come from the second process, which is just this second reading. Okay? Okay, so the work on deriving keys from noisy sources started, I guess before I was born, with interactive protocols for key derivation from qubits. This is by Bennett, Broussard, and Robert in '85. So here we think of this baby wanting to log into Facebook, and what they would do is they would give their initial reading W0 to Facebook because, well, they don't have any privacy anyways. And then when they have a new reading W1, they would engage in an interactive protocol, and they would get out a cryptographic key. And this protocol they engage in could be either information theoretic or computational. We heard work earlier today about how to do this computationally. Well, how to do identification computationally, and then it's not hard to derive a key once you've done the identification task. Okay, so note here, you have to store your initial reading W0 at the server. So in a setting where I'm trying to, say, log into my phone, this isn't appropriate because you need to have trusted storage here for W0. So if I wanted to authenticate to my device, keep something on my device to unlock it, we don't want a solution that stores the initial reading. Okay? So what fuzzy extractors do is they're a pair of algorithms. You have an enrollment algorithm called gen or generate. This takes a measurement W0 from our source, locks it up in a random key R, and a non-secret value P. Okay, so we take our initial reading W0, we get a key out R, and a public value P. And then we have a second algorithm called rep or reproduce. This gives us the same key if the distance between W0 and W1 is less than T. So these guys are close. We get the same key out. Now, importantly, you note that reproduce is taking this value P. So it's taking this public value that we use as advice for what the initial reading is. Okay. So the security is that the key should look uniform even given P. Note that this problem is very, very easy if you assume that P is hidden. You just write the key and the initial reading in it. So really the whole goal is to do this when P is a public value. And we want security as long as the source is good enough. What I mean by good enough is going to change throughout the talk, so that's why I'm not pinning it down yet. So I'll say traditionally, security is defined information theoretically. This will also change throughout the talk. Okay, so we have two competing goals. The first is we want to handle as many sources biometrics as possible. So kind of the natural definition is that you want to start from a source that has high bit entropy. It's, say you can't guess the initial reading with probability more than 2 to the minus k, or it's 2 to the k hard to guess. Okay? So we think of this source as having entropy k as a minimum condition. You're not going to get a key better than security k if this isn't true. Okay. The second is we want to handle as much error as possible. We want to say accept any W1 that's within distance t of W0. Okay? So most previous approaches to deriving keys from noisy sources, they look at these two parameters. They say how much entropy do you have and how many errors do you want to correct. And then they say this is the key we can give you. So because of the Hamming, the sphere bound that was discussed earlier, these approaches give you no security if the number of errors you want to correct is larger than your starting entropy. Okay? In particular, this is true for the iris. And this is why nobody's had provable security from the iris, as far as I know. People have kind of done heuristic analysis, but nobody's actually said this is a secure construction. And so I'll call this condition more errors than entropy. Okay? So what our contribution is going to be is we're going to present a series of lessons on how you can construct fuzzy extractors when this is true. give the first constructions of fuzzy extractors when this is true. We're also going to give something called a reusable fuzzy extractor that can be enrolled multiple times. And then I'll give some preliminary results on what this tells us about the iris. Okay. Just as a refresher, I think we've had this already today, so I won't go too much into it. The way a fuzzy extractor is typically constructed is we derive the key using a randomness extractor or a hash function. Universal hashing is fine here due to Carter and Wegman. And then kind of the magic sauce has always been correcting errors using something called a secure sketch. Fuzzy commitment, fuzzy sketches are all kind of different names for the same core thing that's going on. And this name was introduced by Dodos, Ostrovsky, Reason, and Smith. Okay, and this is just a way to give recovery of the original W0 without leaking too much information. Okay. Good. Okay, so we've already had this once today, but kind of the most well-known approach to this is called a code offset sketch. So we think of, it's basically a one-time pad, except the randomness you're using has some redundancy in it. It comes from an error-correcting code. So what we do is we have our initial reading W0. We want to hide this in P. We take a random code from a code word. We sample this as C. We add this to our initial reading W0, and we store this value. So this is a one-time pad, except that C isn't uniformly chosen. It's chosen from some code word. And what this lets us do is when we have a subsequent reading W1, we add this to our public value P. This gets us close to our original code word. We can decode this using the decoding algorithm, our code. And once we have our decoded value back, we can get W0. Or we can just directly hash this code word. Either way works. OK, so decoding succeeds. We get our W0 back. But if we live somewhere far away, so if it's hard for an adversary to find a nearby reading, then we map far away in the metric space. Decoding hopefully doesn't give us anything useful. OK, so our goal here is to minimize how much this public value informs on W0. So it has to have some information about W0 because it's allowing us to reproduce W0. OK. So this is kind of standard ways these things are constructed. This is how they've been done for about 10 years. OK. So a few slides ago, I introduced this condition that I called more errors than entropy. So I said that you want to correct T errors, which is larger than the starting entropy of your source. Now, I don't know. This might not be a possible thing to do. I might just be a crazy person. So let's consider this distribution for W0. So these are all the possible initial readings of somebody's biometric. Let's say that this distribution has 2 to the k points for some k that's probably about 4 here. We might hope to extract from this distribution, get a good key from this, because all the points are far apart. So there's no real need to deconflict what the original reading is. So if I see this value W1, at least information, theoretically, it's clear what the initial reading would have been. It's this point right here. On the other hand, since kind of the number of errors we want to tolerate is larger than our starting entropy, it's possible that our distribution looks very different. It's possible that our distribution is all close together. Okay? So say these are all the possible readings for our biometric. And we'll call this distribution on the right V0. Now, all I've done is I've pushed all the points close together. They're the same number of points in each distribution. And I wanted to support the same number of errors. OK. Now, an adversary, since they have this public value, is allowed to run the second reproduce algorithm on any point they want. This is the advantage they get by us publishing this value. Okay? Which means they can run reproduce on the center of this ball. Because on the right, these points are all close together, they will always learn the key. Because this V1 is close to every point in the distribution. Okay? So on the left, this doesn't seem like a big problem, because the chance of them picking kind of a nearby point seems pretty low, because our points are far apart. So that doesn't seem like a problem on the left. But what it does tell us is that key derivation may be possible on the left, but it's impossible on the right. It's impossible when all the points of our distribution are close together. And so what this tells us is that if we want to derive keys from a biometric that we want to handle more errors than the starting entropy, we need to consider more than just the entropy of the source. Okay? So we want to look at some other properties of the distribution. Questions to this point?
So I guess what you're saying is that it's a theorem, and you're actually saying there exists a source with entropy k where it's provably impossible
Yes.
to have a fuzzy extractor.
Right. And so if your fuzzy extractor is telling you worst case security, it's saying we get security for all sources with this much entropy, it cannot give you any security. That's what I'm saying. Okay. So what I want to say is that we should be exploiting the structure of a source beyond just its entropy. And in order to do that, we need to understand what structure is helpful. Okay? Okay, so the minimum necessary condition to get keys out of a physical source is that the weight inside of any ball you can draw in the metric space, and I mean the weight of different possible W0 has to be small. Okay? So, and the reason for this is just if the weight inside any ball is noticeable, you can run reproduce on the center of that ball and get the key out. And this has to happen with small probability. So we're going to define a new quantity called the fuzzy min entropy of a distribution, which is going to be the log of the probability of the max weight ball. Okay? And fuzzy min entropy, this is actually stronger than the previous statement I made. Fuzzy min entropy is necessary to derive keys from a distribution. It models kind of security in the ideal world, where all you're doing is giving the adversary access to this reproduce algorithm. Okay? So a natural question is whether fuzzy min entropy is sufficient to build a fuzzy extractor. So in work with Raisin and Smith, we show if you know the exact distribution of your physical source, then yes, this is sufficient. So we build a fuzzy extractor for any distribution. This is a non-constructive approach. We need to know the entire high min entropy distribution. So this is not of any practical importance. But kind of more interestingly is that in reality, you don't actually know what your high entropy distribution looks like. If I have a distribution of 2 to the 200 points, I can't know the entire distribution, right? We've seen some number of irises. I don't know what future ones are going to look like. I may have some model, but I don't have this thing completely figured out. So it's imprudent to assume me as a system designer and the adversary have the same view of what a biometric looks like. I know some statistical properties, say of the iris. The adversary may have more information. Okay? And so the way this is typically dealt with is we assume that the adversary knows more about the distribution W0. And so we provide security against a whole family of distributions. And we say our fuzzy extractor is secure as long as our distribution W0 comes from some family V. And so we get security for any distribution in this family. Okay? So what we show is that there is a family of distributions where every distribution has fuzzy min entropy that no fuzzy extractor can secure. Okay? And this is kind of a more surprising result. And the way I interpret this result is that distributional uncertainty comes at a real cost. If you don't know what your biometric looks like, this can in fact keep you from getting security at all.
Is this a computational bound? Can you explain more what this is?
I'm going to go into this bounds. So yes. OK, so I'm going to go into some math for a second. I'll tell you when to come up for air if you don't feel like going with me. Yeah.
Quick question. When you say source, you mean one person or all the population?
I mean the biometric. So I'm thinking about.
I'm talking about
Yeah.
iris, but
Yeah.
iris is all readings of one person?
No.
All readings
All people. So I'm saying if there's some uncertainty in how the iris looks, the whole distribution across people, it may not be possible to get security
You
for.
can approximate the distribution. The question is how accurate you should.
Right. And so what I'm saying is if the adversary has more information about it than you do, there could be a big problem. Okay? Okay. So the negative result I'm going to show is 4 secure sketches. I'm going to show the impossibility of building a secure sketch. We also have a negative result for fuzzy extractors, but it's more complicated. So I'm going to show the simpler one. Okay. So what we're going to do is describe a family of distributions V, and we're going to show for any fuzzy extractor, secure sketch. For most distributions in this family, they're going to have, for any value P of the secure sketch, there's going to be little entropy remaining. Okay? Yeah, so that's what I said. Okay. So the way this game works is that an adversary specifies a distribution family V. Okay? And our goal as a system constructor is to build a secure sketch for this family V. So we want the min entropy of every element in this family to be high, conditioned on the secure sketch value P. Okay. So before we consider a family, I want to just look at a single distribution, what a secure sketch looks like. So we consider a single distribution. We know that for the public value P, the actual point we encoded has to map to itself. This is just functionality. So the recover of W0 is W0. Furthermore, we know for any nearby value, it also maps to it. This is the fuzziness that we get. So that value maps to it, and then all these points map to it. So I'm going to call this an augmented fixed point. So the value P pins down augmented fixed points in the metric space. It specifies a number of them. Our goal as a system designer is to make as many augmented fixed points as possible, because this maximizes our entropy. Because only augmented fixed points could be possible values for W0. Okay? So let's say we've chosen these points as augmented fixed points. These fixed points have to be at least distance t apart, and this is just by simple coding bounds. So they're an exponentially small fraction of the space, no matter what. Okay. So we're now going to go from a single distribution to a family. And we're going to show that it's hard to include points. For most distributions in this family, it's hard to include many augmented fixed points. Okay. Okay. So the sketch algorithm has to choose where to set augmented fixed points based just on W0. Okay? So what we're going to do is for a particular input value, W0, we're going to build a family that has many possible distributions for each W0. Okay? And what this means is that as the sketch algorithm, I can't decide what W0 is based on my initial reading. So I get some W0. It could, and I'm colorblind, so I'm probably going to mess up colors in the next few slides, but just go with the labels I give them. So it could be this blue distribution, could be this yellow distribution, it could be, is that red or green? I have red. You sure that's not green? Oh, that's
You can run a protocol.
That's the red distribution. So, so I receive this W0, and I know I want to make W0 an augmented fixed point, but I don't know what the rest of the distribution looks like. It could be that, this, or this. Okay? So really, from my point of view, the distribution looks like this. I'm trying to make all of these values augmented fixed points. Okay? But the adversary knows the particular color that was given because it knows the distribution. And these distributions, the way we construct them is we use affine lines. They share only this one point. And so what this means is we have to, the sketch algorithm is trying to include augmented fixed points from all distributions that have W0 as a support, and this is really hard. So let's say these are the viable points we set. Once we know the color, we can eliminate a lot of these, and then we have combining the color with the public value P, our search case space gets very small. And this is true for any choice of points, any p-value we use. So if we use this as our p-value, this still holds. The two pieces of information, the public value p along with which distribution was used, can be combined to remove all security. And I'm not exaggerating with how many points. For this family, Sketch and Rec can't provide more than 2 bits of security. Okay, so this is kind of says that distributional uncertainty is a real problem in building a secure sketch or a fuzzy extractor. So these things I've defined information theoretically because they use coding tools, but there's no real need to provide information theoretic security. And the counterexample I showed was very much information theoretic. Oh, by the way, I'm done with math for a minute, so if you want to come back. So this is our second lesson, is that we shouldn't define these things information theoretically.
Not necessarily, right? I mean, the same phenomena happens in deterministic randomness extractor. Another way that you can go about it is say, let's consider specific families of distributions from which with sufficiently high entropy from which we can extract.
Sure. Right. It could be I provided one family that's a counterexample. It could be for the practical family that irises come from or all biometrics come from. This isn't a problem. There are some other things, other properties that we'll achieve that I also don't know how to do information theoretically, but I don't have a matching. So like one of the families we provide a construction for, we can't do information theoretically, provably. But that doesn't mean for all practical sources it's not possible. So these are guidance. Go ahead.
So do you have the characterization? I mean, like,
Not in the same, right. Not in the same way we do for randomness extraction. Right. I can't say that, right, min entropy is necessary and sufficient for randomness extraction. I can't provide the same kind of, I can say fuzzy min entropy is necessary and sufficient if you know the distribution exactly, but you don't need to know the distribution exactly in the randomness extractor world, whereas it's a new problem here. Okay, so we have another result in this work with Meng and Raisin that says the natural definition you'd use for a computational version of a secure sketch, defined using a pseudo entropy instead of min entropy, is also limited in the sense that we can build a sketch with information theoretic security from one that provides computational security. So our negative result actually translates to this type of computational object as well. And so this is our third lesson, is that we shouldn't use secure sketches. Kind of for this property we're trying to get. They're perfectly fine for high-end. Secure sketches work very well for high entropy biometrics, because kind of the loss you pay there is inherent and you can't avoid it. For low entropy biometrics, they may not be the best thing. Okay, so from here I'm going to combine these lessons and provide a new construction that actually handles these things. Okay, so in this construction's work with Canetti, Paneth, Raisin, and Smith. So what we're going to do is we have our initial reading W0, which is a sequence of symbols. In this case, we're going to say A1 through A9. And we're going to encrypt our key R using parts of our initial reading W0. So what we're going to do is we're going to take random combinations of these symbols of W0. And I'm missing some letters, but let's assume there's a few more letters here. And we're going to, I'm missing the, one second. Sorry. I didn't mean to start from there. Okay, that's fine. So what we're going to do is we're going to take our random key R and we're going to lock it under each one of these combinations. And I'll tell you in a few slides what this lock actually is. So we're going to take this R, the same R that's going to be our key, and we're going to lock it using a bunch of combinations taken from W0. Okay, so this R has gone away. So what we store as P is all of these locks and the positions of the symbols needed to unlock them. So we forget the actual values that were used, so the actual initial readings of W0, but we keep the positions we used. And this is our public value, is all these locks and the positions we use. Okay? And so to reproduce, what we do is we have this new reading W1 that has a bunch of errors. We don't know where they are. I've illustrated them in yellow, but they're in some positions. And we just take the symbols we were told to take, and we try and unlock each of these locks. And since I drew this animation, there's one of them that doesn't have any errors in the combination. So hopefully we can open at least one lock and get our value R out. Okay? So what we need to get good error tolerance out of this is we need that at least one of these locks opens with high probability. What we need for security is that each of these combinations should be hard to guess. So we need that when you sample symbols from this distribution, it preserves enough entropy for this to be true. Okay. Okay.
Why is it enough that just one unlocks? Because you'll have lots of
Functionality? Or
yeah, functionality even.
We keep the same key in each one. So all we're doing is,
But how will you be able to tell which one is the one that's unlocked correctly? You'll have a bunch of answers. You'll have an R1 and an R2 and an R3.
well, let me describe what unlock means, and it'll hopefully be a little clearer. Okay, so what we want ideally out of a lock is the following program. If the input's the combination, you give me out the key, otherwise you give me nothing. Okay? So this doesn't answer Guy's question, but in the random oracle model, you can, without the integrity check, you can just hash your combination and add it to the key. Ideally, what we want is an obfuscation of this program. What an obfuscation does is it preserves functionality, but it hides the program. This specific program is called a digital locker. A digital locker is the obfuscation of this program. It's equivalent to an encryption of R that's secure when you use it multiple times with weak and correlated keys. They're practical, and you can add this integrity check by basically adding a second hash. And there's constructions in the random oracle model are based on discrete log assumptions. It hides R as long as the input can't be exhaustively searched. So as long as you can't check what the combinations are, you're not going to get R out. So you might ask, if you're going to use obfuscation, why bother? If you've been paying attention to crypto in the last 2 years, you've heard a lot about obfuscation, you might say, well, what we really want is this program. If the distance between W0 and our input point is less than t, you output the key, otherwise you output nothing. Okay? And there is a construction from crypto last year that obfuscates this program. It's based on multilinear maps, has a very strong assumption, and it's currently very impractical. So if obfuscating this program becomes significantly cheaper, it will solve the key derivation from noisy sources problem. Okay, so this construction handles sources with more errors than entropy. The theoretical bound says that it can correct less than a constant fraction of symbols, but I'll come back to this in a second. We have two other constructions in the paper that I'm going to skip for now for time reasons. But I told you about this computational construction for two reasons. The first is it has a really nice problem called reusability. And this allows our biometric source to be enrolled multiple times with independent services. And so what I mean by this is I can take multiple readings of my iris, W0, W0 prime, double prime, get multiple keys and helper values out. So this service is generating these things. And any particular key is secret given all the other values in the system. So it's secret given all these public values and all the other keys.
You assume that different measurements inject sort of different errors?
That's a good question. Next slide. So let me skip that for a second. In the past, what they've done is they've assumed that the different readings were, say, isometric permutations of the original, or there's never been a construction that assumed, say, normal noise. They assumed some very strange noise models between the different readings. In our construction, the only thing we need is that these readings are all sources that we can support. So if you look at the marginal distribution of each reading, we provide security for them. And this is kind of the best thing you could hope for. No. They could be exactly the same. They could differ by 1 bit. One could be the square of the other. The only thing we need is that we are secure on each one on its own. Okay? Okay. And this is kind of the strongest type of correlation that's been allowed between repeated readings. And the way we get this is essentially because the obfuscation we're using doesn't leak any information. The only way to get something out of these locks is by completely unlocking them. Okay. So the second reason I told you about this construction is that it looks promising for the iris. So what I said for security of our construction is that we need samples of our iris code bits to have high entropy. And kind of our first experiments, we took 100-bit samples of the iris code. It looks like they have about 60 bits of entropy. So they don't have full entropy, but significantly higher entropy rate than...
How do you measure that?
Okay. So entropy calculation is not something you can do. This is similar to what Rita talked about earlier. What you do is you take a sample, and then for an entire population, you look at the Hamming distance between different people, and you fit a binomial distribution to the Hamming distance curve, and you say, what is the variance, and how many degrees of freedom should it have? It is possible to fool this calculation. This is what people use as the degrees of freedom argument. Okay. Right, so the fact that an iris has 250 bits of entropy, I have no way of knowing if that's true or not to start with. Okay, so, but we use the same calculation that they use over the whole thing. So if we take a 100-bit sample of an iris code, it has about 60 bits of entropy, which isn't kind of as strong as we would want, but it's something to start with. So we need to unlock at least one lock with high probability. So if we want to support about 10% errors, which is, I think, what you need for user applications, we need about 170,000 combination locks, which sounds like a lot when I say it, and maybe it is a lot. But this is kind of about 100 megabytes of storage. So on a phone, this is reasonable. On a remote server, probably not, but there are other techniques if you have a server with trusted storage. So kind of the reason I call this a first look is there's a lot more work to do on the statistical properties and making sure that sampling of iris code bits actually fits the structure that we need. But this looks like it's going to be promising, not to give us, say, 250 bits of security, but something non-trivial from the iris, which I don't know that anybody has achieved before.
Now, asymptotically, it doesn't look too good, right? If k is larger than t, t is larger than k,
Yeah.
then probably you're going to get less and less of these.
So
Probability of a key that is.
right. So the asymptotics say it shouldn't work on the iris. It just kind of happens that the numbers do. So the asymptotics say we can't correct a constant fraction of errors, but we can correct 10 or 15% on the iris.
There's a movie now on YouTube what asymptotically and okay.
Yeah. But it's kind of the key thing for the iris is that it has very low entropy overall. There appears to be a lot of correlation. But if you look at kind of subsets of bits, they appear to be independent. And that's the property we're using, is that small subsets of bits do in fact look independent. And this correlation only comes in when you consider many bits at a time.
One must go back and try to model this and use this to get better fuzzy extractors. Right? Like assume that your distribution doesn't only have high mean entropy, but also independence between bits.
Yeah, I mean, that's what we're doing, is we're using additional structure. We're using entropy plus the fact that when you sample bits, it preserves entropy. Yeah. Yeah, this whole thing is how can you build fuzzy extractors using additional properties of your distribution beyond just their entropy. Okay, so
No, but here we're using a random walk, right?
we didn't have, we were using, okay, so we have one construction that's information theoretic and just uses these additional properties. We have two other constructions based on point obfuscation, which can be instantiated using random oracles. They can also be instantiated using discrete logarithm.
Let's go back to information theory. So even in the information theoretic setup, if you assume these additional assumptions, then you're already making proof.
That's right. Yep. So we get some improvements just by assuming something about the distribution. We get more by going to the computational realm. So this reusability we get in the computational realm. Okay. So these lessons can somewhat be applied independently. We combine all three to get something, but I think they're all useful on their own. So you want to exploit some structure in your source beyond just its entropy, provide computational security. Don't aim for full error correction. The fact is you can do error correction in a different space than your biometrics started in, and we get improvements out of this. We can cover sources with more errors than entropy as long as they have some additional properties. Get reusability for fuzzy extractors, and we have some promising results for the iris, although they're very, very early, and I'm very hesitant to talk about them. And with that, I'll stop and take questions.